Hey everybody, today we're in section 5.2 of our trig book, and in section 5.2 we're going to talk about verifying trig identities. I'm going to show you how to perform operations on trig expressions, and we'll also talk about some algebra strategies you can use to verify identities and exactly what it means to verify an identity. So let's get started and look at a few examples. This is number 1 from the homework exercises in section 5.2. It says, perform the indicated operation and simplify the result so that there are no quotients. And so this is very similar to what we were doing at the end of the last section. Here we have cotangent theta plus 1 over cotangent theta, and what we really want is to perform this addition. And remember I said last time that the only way to perform addition and subtraction on things like this is really to just use common denominators to get the terms combined. So here we need a common denominator. And since this denominator is cotangent theta, I also want this one to be cotangent theta. So I'll multiply this term by cotangent theta over cotangent theta. And then we can combine. So the top now is going to be cotangent squared theta plus 1. And the denominator is going to be cotangent theta. Okay, now let's think about what type of identity substitution we could use on the top expression. This looks like one of our Pythagorean identities that we are supposed to have memorized. So you should know that cotangent squared theta plus 1 is equal to cosecant squared theta, and then the denominator will still be cotangent theta. Okay, so now we're better off than we were because we have performed the addition, and all that's left now is to simplify so that there are no quotients left in the answer. So I think the first thing I would like to do is get this out of the terms of cosecant and cotangent, and let's put it in terms that we're a little more comfortable with. So I'm going to move the cosecant squared to the denominator, use a reciprocal identity to write that as sine squared, and I'll move the cotangent to the top and use a reciprocal identity to write that as tangent. Okay, so you see what happened here? The cosecant squared went to the bottom and became sine squared. The cotangent theta went to the top and became tangent. Okay, now I still need to get this denominator simplified away. So let's change tangent to sine over cosine, and then sine squared will stay there. And now I can reduce sine over sine squared is going to cancel the sine from the top and leave 1 sine theta in the denominator. And so what we have now is 1 over sine theta times cosine theta. And now that we have it simplified this far, it's easy just to use reciprocal identities to bring both of those functions up to the top. So sine theta will go to the top and be cosecant, cosine theta will go to the top and be secant. And there we have it. So the addition has been performed, and we have simplified the answer so that no quotients appear. Here is another example from the homework exercises, and this one has the same instructions, and it starts off secant x over cosecant x plus cosecant x over secant x. And it is another addition problem, so the way to go about it is to get a common denominator. And you could certainly use cosecant times secant as your common denominator, but I find most people are a little more comfortable if everything that we do is sines and cosines instead of secants and cosecants. It's just a little more familiar. So let's use reciprocal identities here to change cosecant to sine. We'll move cosecant to the top, it'll be sine. We'll move secant to the bottom, it'll be cosine. And we'll do the same thing on this term. Move secant to the top, it'll be cosine. Move cosecant to the bottom, it'll be sine. Okay, now you can see that our common denominator needs to be cosecant x times sine x. So what I'll do is I'll multiply the first term by sine x over sine x, and I'll multiply the second term by cosine x over cosine x. And you can see how now that's going to give us the same denominator in both fractions. And so now what we can do is combine the tops here. So the top of this fraction is going to be sine squared x. The top of this second one is going to be cosine squared x. And the denominator is sine x times cosine x. Okay, now this is one of our Pythagorean identities. We know that sine squared x plus cosine squared x is 1, so I've made that change. And now the only thing left to do is to eliminate the quotients, so we will use reciprocal identities to pull these two functions up to the top. So sine goes to the top and becomes cosecant, cosine goes to the top and becomes secant, and so we end up with the same result actually that we got on the last problem. And I just want to point out to you that these were in fact the same two problems, they just looked a little different. So look back here, after we changed our cosecants and secants to sines and cosines, this is cotangent and this is the reciprocal of cotangent, so this is basically 1 over cotangent. So that's the same problem that we had in the previous slide. So I just wanted to point that out to you, that sometimes problems that look very different actually are pretty similar. And if we had gotten here and changed this to cotangent plus 1 over cotangent for our next step, instead of getting a common denominator, then it would have been the same problem. So, you know, a lot of times you have choices when you're working problems with identities. You and I might work the same problem and go about it two entirely different ways, but both get the right answer. Okay, here we have yet another homework exercise. And so this one says, same instructions, perform the indicated operation and simplify the results so there are no quotients. And the indicated operation here is to square this binomial. So let's write it out like a binomial times itself so that we can see how to do our FOIL steps. So, you know, when you multiply a binomial times itself, you use FOIL. So let's do first times first, that will be sine squared alpha. Outer times outer will be minus sine alpha cosine alpha. Inner times inner is also minus sine alpha cosine alpha. And last times last is plus cosine squared alpha. Okay, so you know what happens after you FOIL, you have to combine like terms. We also always need to keep an eye out for chances to use our Pythagorean identities. So notice here I have sine squared alpha plus cosine squared alpha, and because we've memorized our Pythagorean identities, we recognize that sine squared alpha plus cosine squared alpha is 1. And also we see here that we can combine like terms. So minus sine alpha cosine alpha minus sine alpha cosine alpha becomes minus 2 sine alpha cosine alpha. And so we have completely fulfilled the instructions here. It said perform the indicated operation, which we did, and simplify the results so there are no quotients. And I certainly don't see a quotient here, because a quotient would look like we would have a division sign or a fraction. So we don't have that here, so we appear to be done. Now, very often when you're verifying trig identities, you'll need to factor an expression in order to reduce. And so you always want to be on the lookout for trinomials that will factor, or a difference of squares that you can factor. And so here in this example, it just says factor. There's nothing else going on. And we see sine squared theta minus 1. And so recognize that this is a difference of squares. I'm sure you remember from algebra factoring things like x squared minus 9. And so you remember difference of squares. Well, this is a difference of squares as well. And so what we're going to have is two binomials. First times first needs to be sine theta times sine theta. The signs are different. And last times last is 1, so that's going to need to be 1 times 1. And so you see here a sum and difference of the same two terms. So this is factoring a difference of squares. And if you look at this next example, this is a trinomial, 3 terms. Remember, when you factor trinomials, you're trying to reverse the FOIL process. So let's lay out our two sets of parentheses. First times first is 2 sine squared x. So that's going to need to be 2 sine x times 1 sine x. Then last times last made a positive number, so that tells us these signs are the same. And since they need to add, the outer plus inner needs to add up to a positive, these two signs both need to be plus. And then last times last needs to be 1 times 1. And we just need to make sure that our outer plus inner adds up to 3 sine x. So outer would be 2 sine x, inner would be 1 sine x. 2 sine x plus 1 sine x is 3 sine x, and so this factoring is complete. Now we are almost ready to start verifying identities, so let's talk about what that means. Verifying an identity means to prove that the equation is true for all angles. What we're not doing is we're not solving the equation. We're not going to be able to treat it like an equation, because what we're trying to do is prove that it is an equation, that both sides are in fact equal for all values of the angle. And so we won't be multiplying both sides by 2 or anything like that. What we're going to do is use algebra and substitutions with trig identities to make one side look like the other side. So we might use common denominators to transform the left side so that it looks like the right side of our identity. Or we might take a sine squared theta plus cosine squared theta and trade that out for a 1 like we have seen in previous examples. So all of the identity substitutions that we've been practicing with and all of the algebra that we've been practicing with, they're both going to come together here and help us to prove that the left side of an equation is the same as the right side. So as we go along, what I want you to do is we'll be working on one side of the identity, and so you'll pretty much have a blank on the other side, and what I want you to do is list the steps that you're doing and the substitutions that you're making, so that if somebody needs to look at your work, they'll be able to see what you were thinking as you were doing all of these steps. Because sometimes people get lost in their own steps and they don't really know how to backtrack and find out where things went wrong. So if you make a record of what you think is happening, then that makes it easier for your instructor to help you. Okay, just one more reminder that we are not solving equations here. The procedure for verifying identities is not the same as that of solving equations. Techniques used in solving equations, such as adding the same term to both sides or multiplying each side by the same term, should not be used when working with identities. And that's because you can only do these steps where you do the same thing to both sides of an equation. You can only do it because you know that both sides are the same. What we're trying to do here is prove that both sides are the same. So you can't take for granted that they are. So you really shouldn't treat them like equations. Okay, here are a few more tips for you before we get started with some examples. You've got to learn the fundamental identities if you don't already know them. All of the identities that we talked about in section 5.1, you need to know by heart, and you need to be familiar with the alternate forms of the Pythagorean identities. If you don't know these, you won't recognize opportunities to use them, and you won't recognize them when you see them. So you've got to know them by heart. Some of them will be on your formula sheet, but still, if you don't know them, you won't recognize them when you see them. And another thing is, when you're looking at an identity and you're trying to decide whether to work on the left side or the right side, always try to figure out which side is the more complicated side. It's easier to take something complicated and simplify it than it is to take something simple and complicate it in just the way that's required. So always start with the complicated side. And then as you're working, keep the other side in mind. That's like your destination. So that's going to help you decide which path to take and which substitutions you want to make. So start with the complicated side, but don't forget what the other side looks like. Now, one thing that might be helpful to you sometimes is write everything in terms of sines and cosines. This is not something you have to do on every problem. It's a thing you can do if you think it will help. So write everything in terms of sines and cosines and see what cancels out. This is actually one of my favorite things to do when I'm working with identities. In order for this to be helpful to you, you've got to know how to use fractions. So remember your rules for reducing fractions and for getting common denominators. Also, remember that if you have a product or a quotient, so everything's all one term, you can flip things around using the reciprocal identities and the quotient identities. Another good thing to keep in mind is to watch for opportunities to make substitutions using the Pythagorean identities. Anytime you have a squared function and a 1, that's usually a tip-off that you have an opportunity to simplify things by making a Pythagorean identity substitution. But you will not recognize these opportunities if you don't know the Pythagorean identities by heart. So make sure you memorize those and you're very familiar with them, and that you can recognize them in all their forms, even the alternate forms. Also, keep in mind that if you have a fraction and you have multiple terms in the top, but only one term in the bottom, in other words, not separate terms, you can try splitting that into separate fractions. After you split, each term will get the same denominator, and you can reduce each term separately in its own way. That's something that you can't do when the fraction is all together as 1, but after you split up, you can reduce each fraction separately. Now, I don't recommend that you try this if you have more than one term in the denominator, because it usually doesn't work out. But also, please note that you cannot split up denominators this way. You only can split numerators, and then each fraction you split into gets the same denominator that the original expression had. Denominators will not split up like this. Another good thing to think about if you feel stuck on one of these is any operations that you see, go ahead and do those. If it says add or subtract or multiply, try doing that and see what happens. A lot of times that will simplify things for you. And if there's addition or subtraction, remember that we do that by getting a common denominator and combining terms. If you see distributing or FOIL, go ahead and do that. Also, if there's factoring to do, like a difference of squares, try that, and a lot of times that will let you cancel something out. If you try and nothing cancels out, then just go back to the unfactored state. In this last strategy, we have not seen an example of yet, but if you have for example, 1 minus sine x or 1 plus sine x, or 1 minus cosine x or 1 plus cosine x, a 1 plus or minus a single power of any function, and you would like to do a Pythagorean substitution, you won't be able to in this form because you need a squared function to do the Pythagorean substitution. And in order to get that squared function, what you can do is multiply the top and the bottom of that term by the conjugate of the expression that you have, and that will give you a squared function. And we're going to see an example with that, but I just want to get this on the list as one of the strategies that we can use. Now, please do remember, you need to avoid the temptation to use algebraic properties to verify identities. Remember, you cannot be multiplying both sides by sine theta or dividing both sides by tangent theta or anything like that. You can't do the same thing to both sides. The best strategy is to work with only one side and rewrite it to match the other side. You're trying to make one side of the statement look like the other side of the statement. Okay, here we go. Our very first identity to verify. This one says, prove that the cotangent of x over cosine times cosecant is equal to 1. This is an excellent opportunity for us to use our reciprocal and quotient identities because everything on the left side is all one term. Now notice that the left side is the more complicated side. Obviously the right side is the simpler side. So we'll want to start on the left and try to simplify it down to a 1. Alright, now first let's use a quotient identity to write cotangent as cosine over sine. So this cotangent becomes cosine over sine. Now I also have a cosine in the denominator already, And this cosecant, I'm going to move to the top and make it a sine of x. Okay, now we can use algebra to simplify, so we can cancel out the cosines, also cancel out the sines, and so this whole expression reduces down to a 1, which matches the right side, which is exactly what we wanted, so this identity is now verified. Okay, here's another example for us. This one says cotangent theta plus 1 equals cosecant theta times cosine theta plus sine theta. And remember, we always try to start on the more complicated side, so I think the right side is more complicated than the left. And what we'll be doing then is trying to make the right side look like the left side. In other words, I want to use algebra and identities to simplify this right expression until it says cotangent theta plus 1. Okay, so I think the first thing I would choose to do is distribute. And, there's not always one right step. There could be more than one right step. And in this case, I'm going to choose to distribute first. So cosecant times cosine is here, and then I'll have cosecant times sine. Okay, now my next step is going to be for each term to move the cosecant theta down to the bottom. So I'll move cosecant theta down to the bottom, and it will become sine theta. Okay, now my next step is to use quotient identities and just to simplify. So cosine over sine becomes cotangent, and sine over sine reduces to 1. And now we have a match for the left side, so that's what we wanted, so that's where we stop. Now here is an example where I do see some opportunities to do some Pythagorean substitution because I see a squared function and a 1, but I also see a squared function and a 1 on the right side. Now I think you'd agree with me that the right side is a little simpler than the left because there are no parentheses, but the right side could use a little simplifying too. So I'm going to say that this is an example where we really need to simplify both sides. Now notice that even though we're working on both sides, we're not treating it like an equation. We're not doing the same thing to both sides, but we are going to simplify each side independently. And since the right side is a little simpler, I'll start with it. So notice that 1 minus sine squared x can be substituted for its Pythagorean equivalent, which is cosine squared x. And if you're not sure about that, I hope you'll write down the sine squared x plus cosine squared x equals 1 and rearrange it so that the right side is 1 minus sine squared x, and you'll see that the left side then will be cosine squared x. And that's really all I'm going to do to the right side. I see, I could use a reciprocal identity to flip that up to the top and call it secant squared, but really all I need to do is make the two sides match. So I'm going to see now if I can get the left side to look like this. Okay, so over here I have two choices really. I could distribute the tangent squared, and that would not be wrong, but I see that I could use a Pythagorean identity here, and I know that that usually makes my work a little shorter. So instead of distributing the tangent squared, I choose to make a Pythagorean identity substitution. And so 1 plus cotangent squared x is equal to cosecant squared x. Okay, now let's use our quotient and reciprocal identities to write this in terms of sines and cosines. Tangent squared x will become sine squared x over cosine squared x, and cosecant squared will become 1 over sine squared. And now we can use algebra to reduce. We can cross out the sine squared x's, and that just leaves us with 1 over cosine squared x, which is a match for our right side, and that's all we were after was that match, and so this identity is now verified. Okay, now in this example, take a look at the left side. I've got tangent t minus cotangent t over sine t times cosine t. And on the right side, I've got secant squared t minus cosecant squared t. And let's try to decide what we want to attack first. The right side is a difference of squares, but after we factor it, it wouldn't be very pretty. It would be secant t minus cosecant t times secant t plus cosecant t. So I don't think we really want to mess with that, because doing that would not help the right side look like the left side. However, on the left side, I do see an opportunity to split the fraction. Notice that I have two terms in the top, but only one term in the denominator. And so this is going to be a good opportunity to split this fraction. When we split it, each term will have a denominator of sine t times cosine t. The denominators will not ever split. You can split the top, but you can never split the bottom. Each resulting fraction will have to have this as its denominator. So that will give us tangent t over sine t cosine t, and cotangent t over sine t cosine t. Okay, now my next move is I'm going to use quotient identities to change tangent and cotangent to their sine cosine form. So tangent is going to become sine over cosine, and then I've still got this sine t cosine t in the denominator. And here cotangent is going to become cosine t over sine t, and I've still got this sine t cosine t in the denominator. And now let's simplify each resulting fraction. So here I can cross out the sine t's, and in this second one I can cross out the cosine t's. And that's going to leave us with 1 over cosine squared minus 1 over sine squared, see here. And now look what I've got and look what I want to have. And you can probably see that it's good that we have two terms. We wanted two terms, and now we can just use reciprocal identities. The 1 over cosine squared will become secant squared, and the 1 over sine squared will become cosecant squared. And that's a match for the other side, and so this identity is verified. Okay, this one says cosine minus 1 over sine equals 1 plus sine over cosine. Now this one you might feel like you're in a little bit of a pickle, because you can't do a Pythagorean substitution. If you start on the left side, you've got 1 minus sine x, and in order to do a Pythagorean substitution, you need 1 minus sine squared x. You can't just take the square root of each term and decide that sine plus cosine equals 1. So it doesn't appear that there's anything we can do here, and the same thing here. I guess one thing you might try on the right side is to split the fraction, but splitting the fraction would not help you get anything that looks like the left side. So you might feel a little bit stuck. Well, this is where we can use the idea of a conjugate. And I believe this will be the first time we've seen this type of thing done. What we're going to try to do is make the left side look like the right side, although it would be just as easy to make the right side look like the left. Go ahead and write down your left side, and now let's multiply by the conjugate of 1 minus sine x. So the conjugate is the same two terms but with the opposite sign in between. So I'm going to be multiplying top and bottom by 1 plus sine x. Now in the top, you really don't need to distribute this, because if you do, you'll be sorry later that you did. Just leave it undistributed. But in the bottom, go ahead and distribute, because you're going to like what happens in the denominator. When we multiply these two together, first times first is 1, outer and inner cancel out, and then last times last is minus sine squared x. And you see this is going to give us the opportunity to make a Pythagorean substitution. So 1 minus sine squared x becomes cosine squared x. That's one of our Pythagorean identities. And now you see we can get some reducing going on here. So the cosine in the top cancels out one of the cosines in the denominator. And that leaves us with 1 plus sine x over cosine x after we reduce, which is exactly the right side. That's what we wanted it to say, and so this identity is verified. And again, you might be saying, but how did you know to start on the left? Why didn't you start on the right? And the answer is we could have just as easily started on the right. And I would encourage you to, on your paper, take the 1 plus sine x over cosine x, multiply top and bottom by the conjugate of this expression, and see if you can't make the right side look like the left side. It's very easy. It works exactly the same way that this example worked. Okay, and I believe this is our last example in this section. This one is a little more complicated than the others. You take a look at the left side. We have secant alpha plus tangent alpha over secant alpha minus tangent alpha. We do have a Pythagorean identity that involves both secant and tangent, but we don't have any squared functions here, so we're not going to be able to do a Pythagorean identity unless we were to multiply top and bottom by a conjugate, and you certainly could try that. It's not my favorite thing to do, so I'm going to go a different way, but multiplying the top and bottom by the conjugate of one or the other would certainly be a valid thing to try. The right side is not very simple either. The right side has its own complications, and so what we could do is something like we did before, where if we have two complicated sides, we can simplify both of them and try to make them both match some simplified form. And that's what I'm going to do here. Now on the left side, what I want to do is write everything in terms of sines and cosines, but because I have terms here, it's going to require me to create a complex fraction. I can't move secant alpha down to the bottom of the whole expression and call it cosine because of the terms. But what I can do is change secant alpha to 1 over cosine on its own. So what I've done here is I've taken this top and I've written it as 1 over cosine alpha plus sine alpha over cosine alpha, and now that represents the top. And then for the bottom, I've got 1 over cosine minus sine over cosine. So you see that here. I know it looks worse than it did before, but now you can see the denominators. You see, so now you can see that you can simplify this by multiplying top and bottom by cosine alpha. Okay, so if we distribute, the top will be cosine over cosine, which I've got here, and cosine times sine over cosine, which I've got here. Do the same thing in the denominator. And now let's watch things cancel out. This cosine over cosine will become 1. And here I'm going to cancel cosines, and here I'm going to cancel cosines, and here I'm going to cancel cosines. And so that's going to leave us with 1 plus sine alpha over 1 minus sine alpha. And there's really not anything else we can do to that. That's about as reduced as it can get. Now let's work on the right side. So notice that the right side is a trinomial, so we should be able to factor that into 2 binomials. I'm trying to undo the FOIL process. So first times first is 1, and then the signs here need to be the same. They both need to be positive. And then last times last is sine squared alpha, so sine alpha times sine alpha. Now all over, in the bottom I've made a Pythagorean substitution. I know that cosine squared alpha is 1 minus sine squared alpha. And you might say, well, how did you know to do that? And here's what I'm thinking. In the top, I see a 1 plus sine alpha, well, twice really. So I would like to be able to cancel one of these out. And the only way to do that is to get a 1 plus sine alpha in the bottom. And I know that I can do that if I have a difference of squares to factor. So I use this Pythagorean substitution to get myself 2 terms that can be factors as a difference of squares. And now let's go ahead and factor the denominator into 1 minus sine alpha times 1 plus sine alpha. And now we can reduce. 1 plus sine alpha over 1 plus sine alpha cancels out. And that leaves us with 1 plus sine alpha over 1 minus sine alpha, which is a match for the reduced form on the left side. And so this identity is proved. Now this one, granted, is a little more complicated because we had to do 3 steps on each side to get it to work. But it was really good for you to see the complex fraction thing going on here and the factoring going on here. And I promise you that if you'll review this a few times and you'll think through it a few times, write it down every time, don't just read it, but every time write it down, it will stick, your brain will process it, it will sink in, and you'll be much better at it than you were before. So if you're feeling a little overwhelmed, just go back through the examples one at a time, no pressure, give yourself plenty of time, but it really does help to write them out. Don't just read them, but actually write them out, and it does make a difference, and it will help you to process all of this, and things will start to fall into place. What you're really doing here is you're solving puzzles, and people who are good at solving puzzles are people who have solved lots of puzzles before. So you just need practice, and I would encourage you to get out the textbook and work the odd ones. Snap a picture of your work and send it to your instructor and let him or her see what you're doing, and they can mark it up, give you suggestions. They may see something that you're doing right, but there's an easier way, or they might see some things you're doing wrong, and the computer cannot give you feedback on that. You really need to get that feedback from a person. So give your instructor a chance to help you, and before too long you'll be verifying identities all over the place. So good luck.